All right, so with this section, we kind of wrap everything up pretty nicely here. Up to this point, section 3 dealt with limiting reactants. We said, hey, we have this many grams of that substance, that many grams of this substance, put them together, see what happens. And we had to do 2 gram to gram conversions, and we converted to the same product. We said, hey, what's small? Well, we ended up, that smaller number ends up being this theoretical yield. We haven't put this formal definition here until this point, but that smaller yield, or the smaller number that we got in our limiting reactant problems, becomes our, what we call our theoretical yield. So our theoretical yield is saying, if we ran the experiment 100% correct, we had no mistakes in the lab, this is what we should get in theory. Now, most of the time, we do not get that theoretical yield because there's various reasons. Sometimes chemicals aren't great at reacting. They will react, they're not great at it. Other things include errors from us. We may mismeasure something, we may spill something. There's a variety of factors that could affect and not allow us to get to that actual theoretical yield. But this is saying, hey, ideal circumstances, if we ran this experiment perfectly fine, we would get to our theoretical yield. Okay? Questions? Does anybody still need this? Now, what we obtain during the experiment is our actual yield, what we actually get at the end of the experiment. So if we measure, we got some, let's say some solid, we said, hey, let's measure that product, and we only get, 3 grams, that is what we actually got, all right? So there is a difference between our actual yield and our theoretical yield, and quite often they don't line up. And we're going to see how we tie those things together in the next slide. Okay? Questions? Anybody need this? How we tie these things together is our percent yield. Now, it's a percent, so we'll talk about that. It's kind of like your grade there, a percent. But you're going to take your actual yield, what you obtained during the experiment, divided by what you should have got, which is that theoretical yield. And because it's a percent, you're going to multiply it by 100. So I always give the example of, it's like finding your grade. If I gave a test that was worth 53 points and you got 47 of the 53 points, you would take 47 divided by 53. You press enter, you get some decimal, and you say times 100 to actually see your percent. Same exact thing is happening here with our particular percent yield. Okay? Questions? Does anybody need this? All right, so let's see how we calculate the actual problem. All right, so step number 1, balance, right? We've seen this theme throughout this entire chapter. We have to balance the equation. Balancing means something. Now, on the exam, will it be balanced? Absolutely, you don't have to worry about that. But for notes and homework, I'm going to make you balance to get in that habit. Then we're going to determine the theoretical yield, okay? Sometimes you might have to go through that limiting reactant business. Quite often I don't make you do that. I say, hey, you have X grams of some substance and so much stuff in excess, we don't even have to worry about the other reactant. We're going to convert it to that desired product. And once again, we got to read the problem and say, hey, this is what we want, and convert it to that. And then for problems, you will be given the number of grams that is actually obtained. Okay? In a lab experiment, you would do the lab experiment and you would determine, hey, this is actually what we got when we ran the specific experiment. And don't forget to multiply by 100 because this is the percent when we get to our formula. Okay? Questions? Does anybody need this? All right, so let's go ahead and let's do this particular problem. Okay, so the first thing that we have to do is what? Balance that chemical equation. Okay, So we're going to balance the chemical equation, and we have potassium, our K. Just to the right of potassium, how many Ks do we have? So we got 2 on the left, but we only have how many on the right? 1. So what has to go in front of KNO3? 2. Okay, good. Then the next thing is this. We could do one of 2 things. You could keep it as CrO4, the polyatomic ion, because I see it on the other side. Or if you want to keep it simple here, if we just looked at CRs, how many CRs do we have? We have 1, and over here on the right, we have, okay, so they're good. Oxygens I wouldn't worry about until the end. So that leaves us with Ag. How many Ag do we have on the left? 1 here, because there's nothing behind the Ag, but on the right, how many? 2. So in front of the AgNO3 of the silver nitrate, we need a 2. Okay? Then nitrogen. Because of the 2 out in front, how many nitrogens do we have here? 2. How about in front of the KNO3? How many nitrogens from here? 2. Okay, so they're good. Last thing is oxygens. We got 4 from the chromate, plus 2 times 3 is 6. So 4 plus 6 is 10. On this side, we have 4 plus 2 times 3. So 4 plus 6 is, okay, so we're balanced. All right. We go through this, and now I'm just going to read it, and I'm actually going to stop before we even get to the last sentence. It says potassium chromate is added to a solution containing 0.5 grams of silver nitrate. Solid silver chromate is formed. We call that a precipitate. Determine the theoretical yield of that silver chromate precipitate or solid. All right, I'm going to stop right here because I don't even want to read the last sentence. We have a lot of good information that is given out right away, okay? Number 1, we are given an initial quantity of our reactant. Now, it doesn't say this, but we don't have to worry about potassium chromate because there's so much of it there that it's in excess. We do start out with 0.5 grams of silver nitrate. That's the first thing that I'm going to write down, 0.500 grams of our silver nitrate, AgNO3. And as always, I like to talk through our roadmap, okay? Roadmap says, okay, where do I need to go? Well, it says you need to get the theoretical yield for our silver chromate. So at the end of the day, we're going to go to that Ag2CrO4. All right, so we're going to go grams silver nitrate, 2 grams silver chromate. All right, so that gives you a roadmap, a picture in your head. And so here we go with our conversion. So our conversion, we have times, we draw our line. What unit has to cancel down in diagonal? Yep, grams of silver nitrate. And I've said this now for 2 chapters. If you are not in the middleman moles, you got to get there of that particular substance. Mole over G means we need the molar mass. The molar mass of our silver nitrate, if we look back here, is 169.87. 169.87 in this case, is it going to go on top or bottom? Bottom, because big number with G for gram, so we have 169.87 to 1 mole, and we keep going on with our conversion. So now we have times, we draw our line, what cancels down in diagonal? Yep, moles of that AgNO3, and then we can go to anything we want in the chemical equation, but we got to go to moles.
Silver.
Yep. And we're going to go to moles of that silver chromate. Okay. Mole over mole. Where would we get? Very good. Coefficients. All right. So on bottom with AgNO3, what number do we need to put? Okay. On top with silver chromate, what do we need to put? No, right? 1, because that is coefficient that's listed there. Still not done. We don't measure in moles. We measure in grams. So last step here, we have to say times we draw our line, mole cancels of our silver chromate. Okay, we finally go to grams of our silver chromate, and now we need the molar mass here of silver chromate. It's a big number right below here, the 331.73. In this case, where are we going to put this 331 number, on top or bottom? Top, because it's with G for gram. So we have 331.73 grams to 1 mole, and we turn to our calculators. All right. So in our calculators, we have 0.5 divided by 169.87. I hit enter. I get 0.0029. Number keeps going. Now we got to be careful because it's times 1/2. So diagonals divide. So I'm going to take my number in my calculator still. I'm going to divide by 2. I get 0.00147. Keeps going. Last step here is I multiply by 331.73. And I get this specific number. I get 0.488 grams of my Ag2CrO4. Now, this right here, I want to add just one more little note here. This is what we should get ideally or theoretically. And so this is our theoretical yield. Now, the problem asks, what is our percent yield of this scenario? So I'm going to start out, I'm actually going to write down the formula to percent yield. Remember, percent yield, we just talked about this, percent yield is equal to what we actually got, our actual yield, all divided by what? Yep, theoretical yield. And because it's a percent, we got to multiply by 100. And so at this point, I'm just going to insert our numbers here of this. We calculated, or I should say this. We are given in problems your actual yield. Your actual yield is going to be our 0.455 grams of our silver chromate. And it even says in parentheses, actual yield. So on top here, I'm going to go ahead and I'm going to put 0.455 grams, all divided by our theoretical yield, which is why we did all that stoichiometry, which is 0.488 grams. And we can't forget to multiply by 100. And so when we do this, all we have to do is this. We take 0.455 divided by 0.488. I get 0.93, number keeps going. I multiply by 100. Yep, 93.2, I'll call it there, percent yield. Now, in this class, just due to our equipment and things of that nature, our reactions that we do, a 90% yield and above is pretty good work in the lab, okay? Questions on this? Okay. Does anybody need it? Good. All right, last thing is this. Why do we do this? Well, I've mentioned before, chemistry, the business side of chemistry is a multi-billion-dollar industry per year, right? We got big companies like Dow, DuPont, companies down in like St. Louis, Sigma Aldrich. They spend millions upon billions of dollars producing chemicals. You want to not waste the really expensive stuff, so you'll add more of the inexpensive stuff in the chemical reaction, which gives us more desired product. And make sure all the expensive stuff really reacts. And so again, you got to think there is a business aspect to chemistry. Questions on this?